Last time we introduced the idea of trigonometry, which is all about measuring triangles. And we started looking at triangles like this with right angles in them. And we said that we could look at the angles and the sides in the triangle and see that there were relationships. So if I call this angle over here theta, this is the side, the longest side in the triangle, which is opposite the right angle, so it's the hypotenuse. This side over here is opposite the angle I'm interested in, so I call that opposite. And then this one here is next to the angle that I'm looking at, so this is the adjacent side. We introduced these three ratios. We call them instead of trigonometric, we abbreviate that to trig. The three trig ratios, okay, and they were, to jog your memory, sine, which is opposite on hypotenuse, cos, which is adjacent on hypotenuse, and tan, which is opposite on adjacent. And then we took the first letters of all of these different words and ratios to come up with this mnemonic device. So for sine, sine is opposite on hypotenuse, so SOH, opposite on hypotenuse. Cos is adjacent on hypotenuse, and tan is opposite on adjacent, which is where we got SOHCAHTOA from. So that's how you remember what the ratios are. But what's the point? Like, what do you actually use them for? So that's what we're going to explore now. Now what I've got here is just a pair of triangles, and I've drawn them out with some certain measurements. So here's my ruler, and don't want inches, I want centimeters. Okay, so what you've got down here, I'm just being approximate, I know it's slightly off, but this looks like it's about 8 centimeters. This one here looks like it's about 4. Okay, now what's interesting is that I've drawn this out. If you wanted, you could use Pythagoras to work out what this side over here is. But I'm interested in not just the sides, but the angles. So for instance, if you have a look at this angle in the corner over here, if I place that there, I know my lines are a bit blurry, but that looks to me, I read that as approximately 27 degrees. Okay, 27 degrees. Now this is interesting to me because I wonder if there are other triangles like this. So for instance, here's this bigger one. Now if I again do the measurements, so this side over here, that's 6 centimeters. And if I take this longer side on the bottom, that goes from 1 to 12, so that's about 12 centimeters. Okay. Now if I take this measurement again, what I've got here is that you can actually see, you can make out, it forms the same angle. And you can even see that these triangles look very much alike. It's just this one's a bit bigger. In fact, these are similar triangles. Everything is in the same proportions. You know, for example, this bottom side is twice the length of this one over here. This one is double this one, okay? And they're both right angled. So this is really strange because what I've got here, from the perspective of this 27-degree angle in this triangle, I've got the opposite side and I've got the adjacent side here. Okay. Now we've learnt that one of the trig ratios has the opposite and adjacent side in it. The O and the A, that's for SOHCAHTOA. You can see it's this one on the end. It's tan. Okay. So what this is telling us is that because tan of an angle, like say theta, is opposite on adjacent, in this triangle, this is saying, well, theta in this case, it's this angle over here, that's 27 degrees. Okay. It's roughly equal to, I'm saying roughly because all of these measurements are just approximate. It's equal to opposite, that's 4, over 8. That's the other side here. That's a half. Okay. Now this is interesting when you bring it over here because what you've got is different lengths. Like this is, I know it's similar, but it's not the same triangle. But at the same time, you know, this is still, from this point of view, this is still the opposite side. And this is still the adjacent side. So tan of 27 degrees, again, is 6 over 12. Sorry, I should say approximately. That's a half. Still. So what we can see here is that whatever triangle we're in, I could draw hundreds more, which have the same kind of angle in here, the 27 degrees, and the same proportions, like so. Tan 27 is always roughly a half. Now this is really fascinating. Mathematicians know this. In fact, you can get a calculator out and you can say tan 27, and you don't get exactly a half, but you get very, very close. Okay, so we can take advantage of this to work out some different side lengths and angles. Okay, so for instance, if I come back to this, you know, I used a protractor to measure this out. Okay, but I can actually use my calculator to be precise. Here's the way I would do it. I would say, let's get a new piece of paper here. I would say in that triangle over there, you had tan of theta equals 4 over 8, which is about a half, which is equal to a half, this ratio anyway. Okay. So what you can do is, you can say, look, I don't want tan of theta, I just want theta by itself. Okay, so if you have a look at your calculator, so here's where the sine, cos, and tan buttons are, and just above tan, there's a button that looks like, or just above the tan button, it's labeled like this, tan, and then there's a -1 up there, okay? This is what we call tan inverse, and we can use it to find out this angle, okay? So what I'm going to do is, I'm going to say tan inverse of tan theta is theta, and so I'll do tan inverse of a half over here. So if you're following, I can do shift tan, which will give me tan inverse, and then I put in 1 over 2. Okay, now when I press equals, what happens? We get 26.565, and so on, a whole bunch of decimals, right? This is that 27-degree angle that I was trying to measure out with my protractor, but of course, my protractor is only so accurate, I was kind of estimating. But this is not estimating, this is precise. It is approximately equal to 27 degrees because we were reading our protractor right. But it's far more precise than just to the nearest degree, okay? So we can use this. This is really, really cool. If you know any of the side lengths of a triangle, like say you got this triangle here, you got these side lengths, you can work out the angles. Okay, so let me give you an example question. Here's one. So you've got a triangle like so. Okay, and you've got a right angle over here, a 12, a 15, and then they call this angle down here theta. Okay, now we're going to use one of the 3 trig ratios to work out what this angle theta is, okay? So what we can do is we can say, write out SOHCAHTOA, and we'll refer to that in a second. Now, which sides do I have here? When I look from the vantage point of theta, well, 15 is the hypotenuse because it's the longest side and it's opposite the right angle. So this is always the hypotenuse, whichever angle we've got. This 12 is opposite the theta, right? You can see it's opposite there, it's facing. So this is the opposite side. So then I have to think, okay, out of these 3 trig ratios, sine, cos, tan, which one of these ratios compares the opposite side with the hypotenuse, O and H? And the answer is it's sine. You can see it's got opposite and hypotenuse there. So I can write that sine theta, that's this angle here, is opposite on hypotenuse, okay, which in this case is 12 over 15. Sine theta. I can simplify that a little bit because 12 over 15 has a common factor of 3, so there's going to be 4 over 5 here. So what I do now is I reach for my calculator, and just like before we used tan inverse, in this case, because we're trying to find out this angle in this triangle, we can say theta is sine inverse of 4/5. So you reach for your calculator. There's sine inverse just above the sine button, and I can say shift sine, which gives me sine inverse, and then I can put in 4/5, which gives me 53.13, etc. degrees. Okay, so I'll just round it off to the nearest degree. Okay, so this is really cool. Whichever sides we've got, we can always match them up to one of the trig ratios, and we can use that to find out any of the angles in the triangle.